Hello and welcome to the second part of Lesson 5. In the previous part of this lesson, we talked all about linear and nonlinear viscoelastic constitutive equations, those formulations that link the state of stress in a flowing material to its deformation history. We gave some key results for White-Metzner, for Oldroyd 4 constant and for Phan-Thien Tanner, but didn't actually explain how we arrived at them. Most of the time, you'll probably just use these results as stated, but sometimes you may need to derive similar expressions for other constitutive equations that you need to fit data to. So, what we'll do in this part of Lesson 5 is introduce a workflow to derive the steady shear viscosity for the Phan-Thien Tanner equation. We'll follow a very similar procedure to that used in EPD650 that we used to obtain material functions for upper convected Maxwell. If you can't remember how this was done, it may be a good idea to re-watch that video before watching this one any further. I've put a link to that video in this video's description. If deriving the upper convected Maxwell result is familiar, however, let's make a start with Phan-Thien Tanner. So, in the last part of this lesson, we saw these equations on the whiteboard. The first equation is the constitutive model itself, the convected constitutive model for Phan-Thien and Tanner, and then we had some various definitions of some of the terms in there. Remember, the key thing that we said here is all about that gold coloured term. Z trace tau is just saying Z is a function of trace of tau. That term does not mean Z multiplied by the trace of tau. So, we saw that Z trace tau could take one of two expressions. One is effectively an expansion of the other. We have the exponential term. We saw that that has problems with maxima in terms of extensional rate. But if we do a binomial expansion of that exponential term, we end up, if we take the first two terms, with the linear term that I've put there on the board as well. And I gave you three key results. One for the steady shear viscosity, and one result each for each of the normal stress coefficients, psi1 and psi2. We also said that there's no analytical solution for the steady extensional viscosity. So, what I'd like to do in this part of Lesson 5 is to derive the steady shear flow viscosity that Phan-Thien Tanner predicts. In doing that, we'll also see how we could easily arrive at either psi1 or psi2. Furthermore, we'll also see why there's no analytical solution for extensional viscosity, and we'll also see the form of equations you'd have to solve in order to obtain that result numerically. So, what we're going to do is to derive the apparent viscosity as a function of shear rate for Phan-Thien Tanner. So, what we need to do is to get a bit of a workflow established. It's the same workflow that we used in EPD650 when we were looking at exactly the same problem, only with upper convected Maxwell instead. And there were effectively three steps that we took. Firstly, we made an assumption of the flow scenario that we're looking at, such that we can get the material parameter that we want. We need a shear flow because we're looking at shear viscosity, and so we're going to assume the simplest possible shear flow in the simplest possible coordinate system. So we're going to assume Cartesian coordinates. We're going to assume that I've got a flow in the x direction, and that x direction velocity varies with y direction. Imagine it's effectively flow between two parallel slits, for example. And that allows us to define what our shear rate is. Our shear rate is simply in one dimension, is dvx by dy, and I'm just going to call that gamma dot 0. So that is my shear rate. The next thing we're going to assume is something about the nature of the flow. We're going to assume that the flow is steady, there's no time varying components. We're also going to make this assumption of homogeneous flow. Now, I went over what homogeneous flow was in some detail in EPD650, but just as a recap, this is where the dot product of the velocity field and the stress tensor equals 0. V dot tau equals 0. Now, if V dot tau equals 0, that allows us to simplify the upper convected derivative quite substantially, which gives us a very easy result to work with. So, if that's a little unfamiliar, go and revise that video from 640. The third step of our workflow is to keep it simple. As we go along, we're going to simplify all our tensors. And so we're only going to be including the shear components in our shear rate tensor, big gamma dot in bold, and that's just simply gamma dot xy and gamma dot yx. Both of these are equal because of the symmetry of the problem. Both of the non-zero shear rates is just simply gamma dot 0, as we've defined in step 1 of our workflow. Remember also that when we're doing these sorts of analyses, we need to include all our normal stresses a priori at the start, because we can't assume they're 0, because we're dealing with viscoelastic models where normal stresses will probably be generated. Okay, a bit of time out. So, just to reiterate, if anything that I've said up until this point is unfamiliar, please go and make sure that you're familiar with the 2 videos that I've put there on the whiteboard, and those links will be put in the description to this video as well. Those videos concern looking and dealing with upper convected constitutive equations and also solving upper convected Maxwell for steady shear, which is effectively the same thing that we're doing here except for PTT. So, assuming that knowledge is fine, what we're going to do is just follow our workflow. There on the whiteboard I've put the Phan-Thien Tanner constitutive equation, and I've coloured 4 terms. I've coloured the upper convected derivative of stress, the first upper convected derivative of stress, in blue, the stress tensor itself in red, the shear rate tensor in pink, and the sort of dot product of the sum of the shear rate tensor and the stress tensor as a group in green. Now let's go through each of those 4 terms one by one and simplify them. Let's start with the upper convected derivative of the stress tensor, tau subscript brackets 1. When you look at the video in 640 deriving exactly the same thing for Maxwell, what we can see is that we end up with a form of tau 1 as follows. It features the y direction principal stress in the 1, 2 and 2, 1 positions, and it features the shear stress in the 1, 1 position. So if you can't remember how to get to that, again, please have a look at that video for 640 where we're doing exactly this for upper convected Maxwell, and I spend some time deriving that result. Okay, let's move on to the stress tensor itself. Now, we've got a shear flow, so we need to have non-zero elements of that stress tensor that correspond to the non-zero components of our strain rate tensor. So it's the yx strain rate giving us a yx stress. So that is in the 1, 2 and 2, 1 position there in red on the board. But remember what I said a little while ago is that we're dealing with a viscoelastic fluid. Viscoelastic fluids by their very nature will generate normal stresses and normal stress differences, so we need to include the normal stresses in this tensor as well. So we've got the XX, the YY and the ZZ stress. Okay, let's have a look at our deformation now. We've chosen the simplest shear deformation possible. We have a non-zero deformation rate in the 1, 2 and 2, 1 position, and that's simply gamma dot 0. So there on the whiteboard are the 3 individual tensors as they stand. So my first upper convected derivative of stress, my stress and my strain rate. Now let's deal with the term in green there that's pre-multiplied by lambda. So gamma dot dot tau plus tau dot gamma dot. Now that we've got simplified tensors for both tau and gamma dot, we can simply write this out longhand. And so if we write out each of the tensors, how they dot product together, you get what I've just put there on the board. And so you've got gamma dot dot tau plus, pre-multiplied by gamma dot because that's a scalar and we can take it outside the tensors, tau dot gamma dot. So if you remember how to do the dot product, we're just going to look at the row multiplied by the column. And so if we think about that, let's take those first 2 tensors. Let's take the gamma dot tensor, which is 0, 1, 0, 1, 0, 0, 0, 0, 0, dot product that with the stress tensor. And if we look at how we operate on the elements in the top row and the elements in the first column, we get 0 times tau xx plus 1 times tau yx plus 0 times 0, which gives us simply tau yx in the 1, 1 position in that dot product result. And so if you go through the rest of that dot product operation, you'll see that you get that first tensor there. And then if you repeat the same operation with the second term in the addition, you'll get the second term in the tensor that I've put there on the board for you. Of course, we can add these results together, and what we get as a result is gamma dot times this tensor here. And if we look carefully at that tensor, it features our principal stresses, tau yy and tau xx, in the 1, 2 and 2, 1 positions. So they're symmetric. And also we have the shear stresses, tau yx, featuring in the 1, 1 and 2, 2 positions, and that's symmetric. And so when you've done this operation, we are expecting a symmetric result because all the tensors in these equations are symmetric. And so if you obtain an asymmetric result, just go back and check your dot product because you've probably got something wrong. Okay, so let's now focus our attention on that z term. So we've said that z trace tau is z as a function of trace of tau, and we're going to elect to look at the exponential form of it, which is the more complete form. Remember that the other form was just simply a binomial expansion of the first two terms of this exponential form. So if we're dealing with shear flow, we're going to make an assumption. We're going to make an assumption outright that the principal stresses are small compared to the shear stresses. They're not zero, but they are small. So that means that the trace of the stress tensor, tau 1, 1 plus tau 2, 2 plus tau 3, 3, so that's tau xx plus tau yy plus tau zz, we're going to say is substantially less than 1. Okay, it's an assumption. We may need to revisit that later on. But what that means is that the terms wrapped up inside the exponential are sort of about zero-ish, which in turn means that z trace tau is about 1. And that is why we're trying to make this assumption, because z trace tau introduces a nonlinearity. We'll see that again in a minute. But if we can justify removing that nonlinearity by making some assumptions about the nature of the stresses, then actually we can get an analytical solution for the material parameter that we're looking for. So there's a consequence to this, is that if we're thinking about shear flows and shear flows alone, epsilon's completely neglected. So the only parameter really other than the relaxation time that dominates PTT for shear is the shear viscosity to 0 and also xi. Okay, so if we are happy with that assumption, and again we might need to check that, let's see what result that gives us. So there on the board is the fully fledged constitutive equation with each of the terms that we've discussed. Let's now write it out in long form. So we've got each of those tensors appropriately color-coded with their origin in the full constitutive equation. And what this gives us are four equations, four algebraic equations to work with. Let's write these out. Let's start with the simplest one first. The first equation that we get is that the z direction principal stress, tau zz, equals 0. And we obtain that equation by looking at the 3 location in each of the tensors and just simply adding the terms up. And so the first tensor there in blue is 0, the second tensor there in red is tau zz, the third tensor there in green is 0, and on the right hand side the 3 term is again 0. So tau zz equals 0. So that's a simple equation to deal with. Let's have a look at the next diagonal position. Let's look at the 2 position. So in the blue tensor we get 0, in the red tensor we get tau yy, in the green tensor we get 2 tau yx xi upon 2 lambda gamma dot, and on the right hand side we get 0. And so what we end up with here is an expression that links tau yy, the principal stress in the 2 position, to tau yx, a shear stress. Now that's really useful, as we'll see later. So let's just put that result to one side, and we're going to do the same thing now for the 1 position. And if we look at the terms in the 1 position of all the tensors, we get the expression I've put there on the whiteboard. The right hand side is again equal to 0 because my deformation tensor gamma dot doesn't have any extensional components. On the left hand side we have a sum now of 3 terms. We have a term involving the relaxation time from the first tensor, we have terms involving tau xx from the second tensor, and we have terms involving tau yx and xi from the third tensor. And again, rearranging what that gives us is another way to link the shear stress tau yx to a principal stress, in this case tau xx. So now we can write tau yy as a function of tau yx and tau xx as a function of tau yx. let's look at the final equation. And the final equation can be obtained from looking at either the 1-2 position or the 2-1 position, because we've got symmetry throughout this equation. So I'm going to look at the 2-1 position just because it's easy to draw a purple box there. And what that gives me is an equation where we have a non-zero left-hand side and right-hand side. And if we look at that left-hand side, we have an equation that involves all of the stress terms that we've included. So we've got the two principal stresses, tau yy, tau xx. We also have our shear stress, tau yx. So let's look at this in a little more detail and see what we do. I've rewritten that equation from the 2-1 position there on the board, and I've coloured the principal stresses because, of course, what we can do is we can substitute those principal stresses for the expressions we've already obtained from the 1-1 and 2-2 positions of that constitutive equation. And what that gives us, very nicely, is an equation that only involves one stress, tau yx, is linear in tau yx, and it can be very easily rearranged. So there on the board is that same equation with the tau yy and tau xx terms substituted in. And with a little bit of manipulation, we can find an expression explicit in tau yx, which is nearly there. Remembering what we're looking for is an expression for our steady shear viscosity. Our steady shear viscosity is simply our shear stress divided by our shear rate. And so if we make that division, then we end up for the expression on the board, which gives us eta as a function of gamma dot, resulting from the parameters in the PTT equation. And so that is the key result that we quoted in the previous part of this lesson for PTT for its steady shear viscosity. Now, it's exactly the same analysis to get the normal stress coefficients. I'm not going to do that right here, right now, but we already have all the information from this analysis to write out what psi1 and psi2 are. So you might want to go away and see if you can obtain these two results. Now, final thing. We said when talking about PTT that the steady extensional viscosity didn't have an analytical solution. Let's now look why that's the case and see what we can do about it. So if we're thinking about an extensional deformation, let's assume that we've got, I don't know, a uniaxial elongation. Our rate of strain tensor, gamma dot, might look a little like what I've put up there on the board. The only non-zero rates of strain are on the principal diagonal now. And if we think about the stresses associated with that, because of the way the constitutive equations work, the trace of the stress, tau, is going to be greater than 1. The trace of the strain rate is 0 because the fluid is incompressible, but when we work out what tau is, tau will have a non-zero trace. And so we cannot justify neglecting that z trace tau term anymore, which means that our constitutive equation now becomes non-linear as a result of the tau xx plus tau yy plus tau zz term that will feature in that third tensor. So that is why PTT becomes non-linear in extension. But what we can do about it is that we can simply write out the equations that we can obtain from looking at each position in those tensors and then solve them numerically such that we can get the result that we're looking for. Okay, so a few key points. So this part of this lesson concerned how to derive the steady shear viscosity for the Phan-Thien Tanner constitutive equation. We saw that normal stress coefficients are simply an extension of this analysis, and this whole analysis was based on something that you should have seen before, which is a similar analysis for upper convected Maxwell that was covered in EPD650. We can get the extensional viscosity from the same workflow that we've gone through. We just used different gamma dot and different tau tensors. And the key assumption that we had to make in order to do this analysis in the first place was that the flow was homogeneous and that for shear flow, trace of tau is less than 1.